I'll move my backpack from there. You can also try and just grab a seat at the front. I know it's a little bit uncomfortable, but if you want to like, we could sit on. Yeah. Do you have this? It'll be really fun. I'm sorry,
Okay. All right, San Jose. Thanks. All right. Good.
This is the whatever you see here is being recorded. So yeah, I maybe should have been closer with the camera.
No.
Okay.
Good. All right. Hi, folks. All right. So, I'm Aryan. I am a fifth-year physics student here at U of T, also one of the execs of PhySU, and I'm excited to welcome you to the inaugural undergraduate colloquium for the year. It'll run here, same time, same place, basically every week throughout the year, and I'm excited to see so many of you out here for our first talk, which I'll be giving. So, to summarize very briefly, I spent my summer working at CERN in the Alpha group, which is part of the antimatter physics sector there. And the group in particular is famous for a paper a couple years ago where they found out whether antimatter falls down. And by the end of this talk, you will know an answer to this question. It might not be the answer you want, but it'll be an answer. So on this first slide here, we already have something quite interesting, which is the particle trace that an antimatter particle left through a bubble chamber, which is how we did particle physics back in the days. Essentially, a particle comes in and it leaves a trace. And by analyzing that trajectory, you can find out what kind of particle it is. And so in this case, they noticed that it had the exact same path that a particle with the mass of the electron would make, but it curved in the opposite direction, indicating that it had opposite charge. And so that was how the positron was discovered, which is the antimatter particle of the electron. It has positive charge, but it's otherwise all the same. That was discovered in 1932 by Carl Anderson. So we have a lot to cover today. It's going to be more broad than deep, but I hope everyone finds something interesting. And it also does mean it's tight on time, but if I'm going too fast, please let me know. So I'm going to start off by just talking about CERN as a whole, the accelerator complex, and fun facts about it. And then I'll talk a bit about the physics of antimatter before proceeding to specifics about the alpha collaboration, my work, and of course, the coveted answer. So welcome to CERN. This is the view you see if you arrive on site from Geneva, taking tram 18. This building complex is the Science Gateway, where it's the sort of public-facing museum side of CERN. Obviously quite different from what you see on a day-to-day basis working on the site. So it is the European Organization for Nuclear Research. It was started as the Council and then changed to the organization, but they kept the acronym because OERN sounds kind of lame, I guess. It's founded in 1954 in Meran, which is a village outside Geneva. Looked like this back in the day, and frankly, outside of CERN, it still looks quite a lot like this. This was founded in the aftermath of World War II, where European science and industry was destroyed, and they chased out all their great science talent. There are absolutely no real-world parallels today. And so CERN was created as a way to promote peace and prosperity on the continent and to rebuild its scientific infrastructure. And so specifically, they said that they would not use anything there for military purposes, and that would all be open source. And thanks to that, I get to show you a bunch of pictures from my summer as well. And so there are 25 member states. This graphic doesn't have Slovenia, which was just added this year. And most of them are from Europe and one conspicuously outside. But there are also bilateral agreements with countries from around the world. So if you're a member state, that country pays in to fund CERN, and their citizens also get sort of the highest privileges at CERN, where they can, they make up the permanent staff who run the site, run the basic facilities. But then it hosts, through the experimental collaborations, it hosts researchers from around the world, regardless of which country they're from. And so there are thousands of researchers, and also hundreds of students who come every summer through the various summer programs. Students doing research, but also working on more technical internships, like running the accelerators or even stuff like electrical engineering. And it's a really, really big student program. And so here, just to give you a bit of an overview, we have central Geneva, Lac Léman, and the Rhone River. Around here, you have like the UN and the Red Cross. And then you take tram 18 out to Meran, and here is CERN, straddling the French border out here. This is all on the very western edge of Switzerland. And so, zooming in a bit more, this is the main campus. So you sort of get off here, and then this is one end of site. This is another, and this is about 25 minutes across. And there's another campus you're also not seeing. That's smaller, and I don't really know what they do there. But there's a lot going on inside. Obviously, they have the accelerator facilities here, administrative facilities, and also some other fun stuff, a 24/7 library, a couple of restaurants that serve somewhat decent food, and also a hotel for visiting scientists and students to stay while they're on here. Now, beyond here is the French village of Saint-Genis, which is essentially a bedroom community for CERN scientists. And I bring it up mainly to point out the roundabout in the middle, which is affectionately referred to as the large car collider for the way that people drive around it. And one of my friends was biking through it, and he something happened for which he wrote a Google review on the large car collider, and he, quote, experienced a low energy collision event. And I think he's all right, but you know. But so the major achievements include lots of things, but the discovery of the W and Z bosons, the Higgs boson in 2012, which is very famous and why they created the biggest accelerator there. They first created antihydrogen, and they invented the internet, or the protocols of the World Wide Web, which is commemorated in this plaque. This is another view of site. This like road on the left is sort of my main thoroughfare, and you can see the Alps beyond in the distance. For the summer students, they have a lecture series where professors from around come in and talk about different aspects of experimental particle physics, particle theory, and other things relevant to working at CERN. And they have us in this nice lecture hall, which is the same place where they announced all their big discoveries, like the Higgs boson in 2012. And I really enjoyed participating in this, including getting to meet David Tong, who is even more awesome in person. If you don't know about him, go look at his lecture notes. So before I talk about the accelerators at CERN, I want to talk about why we have acceleration in the first place. It all comes down to making interesting physics happen. Everything seeks low energy states, and since we have this mass energy equivalency, all the heavy particles, you know, the more exotic quarks and such, are very energetic, and they seek to decay down to lower energy states, less massive states, the basic kinds of quarks that make up our bodies. And so to make these more exotic physics, the particles, and to make more exotic processes happen, we need to get things to higher energies, and basically we do that with speed and collisions. And so the first accelerators were linear designs that came on in the 30s and 40s, as well as circular designs I'll talk more into. This on the right here is the first cyclotron at CERN that's now just commissioned and it's a forest piece. This is one of the old linear accelerators that's also just on display. So how do we accelerate things? It all comes down to electromagnetic fields. And so in a linear, so this is the Lorentz force law, which shows you that, you know, you can exert a force on a particle by applying an electric or a magnetic field. And so the linear design is, say you have a particle, you start it off, and it goes through a particular segment where you apply an electric field and that pushes it forward. And it goes through another segment and you repeat the same thing over and over. And these are all synchronized so that when the particle passes through a certain gap, it sees a strong electric field and goes on and on. And these are pretty good designs, but to get higher energies, you need longer accelerators or higher fields. Those are both pretty hard to create. So what about a circle? Now, here, there's some background magnetic field which moves particles in a spiral. And at this gap region here, there is a synchronized electric field which is applied to accelerate the particles. So those particles accelerate when crossing the gap, and then they spiral outward because they have more energy, their circular orbit is larger. And that was the design of the syncocyclotron, which is CERN's first accelerator that you saw. These can get you up to about 600 mega electron volts, where an electron volt is the energy of an electron moving through 1 volt of potential. And so they're pretty good for lots of things. If you want to make like exotic chemical isotopes, they're really useful. Canada has the largest one of these at Triumph in Vancouver. That is useful for a lot of things. But really, if you want to go bigger to like particle physics levels, then you need to go to the synchrotrons, which are essentially constant size rings. So instead of spiraling outward, you're just being bended along a constant circular path by various magnet configurations. And then the acceleration is done by radio frequency cavities, where you have an electric field that is synced up so that when a particle bunch passes through, it experiences a high field pushing it forward. And the cool thing about these is that you can just keep sending the particles round and round and round until you get the energies you want. Obviously, you need synchronized fields, and so that's why they're called synchrotrons. Now, you can't start your particles in this loop. That breaks the closed loop, so you need to inject them from something else, and that's usually done from like a lower energy linear accelerator. So this is like an example quadrupole magnet, so you can see sort of the 4 different configurations around, and these would be to bend and also focus the beam onto a tight punch. This is like 5 lectures worth at the CERN program, so there's a lot of accelerator physics that I'm not covering here. It's a really delicate art, and I encourage you to learn more. So this is the CERN complex. So there are a lot of accelerators. We start off the chain with the 4th linear accelerator, so there have been 3 that have essentially, or first 2 are decommissioned, 3rd one does something else. So the first LINAC gets us here, and then we go into this booster ring, which then sends us to the proton synchrotron, which is the first large synchrotron. It was created in 1959, and it used to do cool science. It's now only meant to get us as a stepping stone to higher energies. I'm slightly amazed it still works. So that gets sent off. Then it gets sent to 1976's super proton synchrotron, and then on to the Large Hadron Collider. It's a large collider. Hadrons are composite particles, protons, and so that's where it gets its name from. And then this giant ring, there are actually 2 beams, and they get overlapped at 4 locations, which are the 4 experiments: ATLAS, CMS, ALICE, LHCb. Each of those is a giant particle detector that like analyzes the collision events for interesting physics. And that's the high energy side, but there are also various other parts of the complex. So there's some sort of off the main beam stuff that I don't really know about. But what's of interest to me is from this proton synchrotron beam, we go up here to the antiproton decelerator, where the protons are used to create antiprotons, and I'll get to that in a second. They're also gone to other things like ISOLDA, where they create rare nuclear isotopes and study them. And it's really, there is so much going on inside. That is just the quickest overview. But the point is, each level in the chain gets you to higher and higher energies, where like the LHC, you're pushing maybe 10 tera electron volts. And for sense of scale, proton synchrotron right on site, SPS, bigger starting to get off site, LHC, circling around, and future circular collider. Maybe they will or won't build it. I don't know how that'll get built, but like just one more collider, bro, So I got to see parts of the site. You can't actually go down in the ATLAS detector while it's running, of course, but this is the control room for ATLAS, where they like monitor the experiment and the collisions. They have a nice little model, a Lego model of the detector, which I found quite cute. There is a giant mural on the side of one of the buildings that is like to scale, and it's like 6 stories tall, which is very cool. They also have a live Higgs boson counter, which as of early June was about 16 million in the total run of the LHC. It's pretty cool. Okay, so that's sort of the high energy frontier. For antimatter, we don't need as high energies. In fact, making positrons, the anti-electrons, are quite easy. There's beta plus decay, where a proton decays to a neutron and it emits a positron, which is required for charge conservation, right? There's +1 charge on the left and +1 on the right. There's also just pair production, which is a process where a high energy photon makes E plus and E minus. Antiprotons, or P bars as we call them, are heavier and they're just more complex objects, so they're harder to make. What we do is take protons from the TS, collide them onto some target, which is an indium rod usually. That creates a whole bunch of things, including antiprotons, which are then extracted and focused into a beam that are then delivered to the facilities. And this happens at 26 gigaelectron volts, which is quite a bit higher than the threshold, but it's still a pretty laborious process. I mean, 10 to the 13 Ps, you can take to the 7 P bars. And so it's quite inefficient. And this here is just a diagram. See, okay, where your protons come in, they hit off that and go on their merry way. That is sort of the basics of CERN. Now we're going to talk about antimatter. And I will say it would have been nice to do this talk after finishing a quantum field theory course and not after having 1 hour of lecture, but here we are. So this is a basic Feynman diagram, which is how you illustrate processes in particle processes in quantum field theory. And so here you have an electron coming in and a positron, and you could say one interpretation, I guess, is they annihilate here to produce a photon, pair annihilation, and then you have pair production where they come back. Time goes along this axis. You can also just interpret this as E plus, E minus scattering off into each other. Okay, so how do we theoretically get antimatter? We have the Schrödinger equation for quantum particles. The problem is that it is very explicitly non-relativistic. You have a first order time derivative on the left, and second order spatial derivatives on the right with that Laplacian, the del squared. And that is an asymmetry between space and time that is explicitly inconsistent with special relativity. So just theoretically, to have a, yep?
What's relativistic?
It means it's the physics of what happens when you move very close to the speed of light. But I mean, really, it's the framework for all of modern physics. And in that framework, space and time are two aspects of the same entity. So they should be treated at least similarly. And so, Dirac, looked to solve this, and he created the Dirac equation, which is noted on this plaque in Westminster Abbey. I don't really care about the details here, but you can notice that single derivative del, which is for both space and time derivatives. So now it's fully first order. And it describes electrons. It actually describes all elementary matter particles, or ones that have spin magnitude 1/2. And there are other equations for your spin 0 or your spin 1 particles. Not relevant here. Now, there is a small problem in that this equation has negative energy solutions, which are bad. Negative energies in physics alone are fine. It's obviously energy is just relative to what you measure. But we know that through interacting with the electromagnetic field, that particles can lose, like an electron can lose energy. And so if it can have arbitrarily negative energies, then an electron would just keep losing energy over and over and over again. And that's kind of ridiculous behavior. We don't see that. And so Dirac had this interesting cope where he thought all the negative energy states were already filled by a sea of electrons. And so because of the exclusion principle, there was no space for electrons to lose energy and go to negative energies. And an interesting aspect of the sea is that a hole would be an absence of negative charge or a positive charge. Now, this was all kind of a mess, and it was eventually reinterpreted that these negative energy solutions are actually antiparticles, so positrons for electrons. And we now know that every standard model particle has its own antiparticle, except for some edge cases like the photon, which is its own antiparticle, but that's neither here nor there. The point is, antiparticles are the same as the original particle, except that their electric charge has the opposite sign, and also their other charges for other interactions are switched. But they have the same mass, the same energy, that kind of thing. And so antimatter fixes a lot of things, and it's very useful. I should mention, so this was done in the late 20s, and the discovery was made in 1932. So it was a very quick follow-up. Now, to discuss the modern problems with antimatter and why we're interested in it experimentally, I want to talk a bit about symmetries. In physics, you have this quantity called the Lagrangian, which essentially incorporates all the dynamics of your system. So, you can have one in classical mechanics where it's just the kinetic minus the potential energy. That gets you all the equivalent dynamics to Newton's laws. You have similar things in quantum mechanics and quantum field theory. The interesting idea is is Noether's theorem, which was created by Emmy Noether, who incidentally was one of the scientists persecuted from Europe. She said that any transformation that leaves your Lagrangian invariant implies a conservation law for your system. So, for example, if your Lagrangian does not depend on your spatial coordinates, it's invariant under spatial translations. That leads to linear momentum conservation. You have similar things for angular momentum, for energy. And just to use an example here, on the second line is the Lagrangian for a classical particle in a gravitational field. And you can see it doesn't depend on time. It's time invariant. And so that implies energy is conserved for the system, which we know to be true. And also, it doesn't depend on the angle, just the distance from the origin. That's rotational invariance. And so that implies angular momentum is conserved, which is also true. Now, what I talked about is just for continuous symmetries, where you can kind of change the system as little as you want. But there are also discrete symmetries, where you can invert the charges of particles. You can invert the parity, and you can do a time reversal. C, P, and T. And I'll discuss those now. So at this point, we're really working in the quantum world, and so we interpret transformations as quantum operators acting on state vectors. And so charge conjugation, typo, it basically just means switching matter and antimatter. So C acting on psi gives you psi bar, which is the antiparticle version, and then C acting on psi bar gives you psi. And so basically, all this does is switch the electric charges and the other charges, and yeah. Parity inversion then is to flip the spatial coordinates. It relates to something called the handedness of a particle, where, as you can see here, say your particle momentum is in this direction, and its spin vector is also in this direction. That follows the right-hand rule, and so that's a right-handed particle. and then the opposite is left-handed. And so a parity inversion switches the handedness of particles. And yeah, you also have a time inversion where you can run things, you can run your system backward in time. And this is a necessarily microscopic phenomenon because, you can look around you and see how time evolution is one way, the universe expands and so forth. So that is really, we can only talk about it at a fundamental particle physics level. But yeah, so these are 3 transformations you can do. And if it leaves the Lagrangian, or it basically leaves the physics unchanged, then it's a symmetry. So we can talk about violation now. These individually are conserved in most normal processes in physics, and I'd encourage you to try to think of something that would violate CP or T symmetry. However, by the 50s, there was evidence of P violation, and so there was an experiment by Cheng-Sheng Wu, who actually has a road named after her at CERN, that would seek to establish this parity violation in the decays of cobalt-60, which were induced by the weak force. And what she found was that the electrons are emitted preferentially opposite to the nuclear spin, as you can see in this diagram, and the nuclear spin is invariant under the parity transformation. You can flip the parity of your system, but the direction of emission is largely the same. And that's a parity violation that really shook the foundations of theoretical physics. So one thing we can do is like, okay, what if we just loosen our conditions? What about we only have symmetries when we do a charge inversion and a parity inversion? In the 60s, there were experiments with other particles called kaons, where they found a very weak violation, like a 0.2% violation. So I'll admit the experiment is a little beyond me, but you can imagine here, maybe the electrons were emitted almost equally in both directions, but like 1 part in 500 was preferentially emitted down, say. That's the kind of level we're talking about. Now, CPT, so the inversion of charge, parity, and time together, is a symmetry of the Standard Model. We know that for any local Lorentz invariant quantum field theory, that this must be an exact symmetry. Local just means that the interactions, can't happen magically at distance. Lorentz invariant means it's a relativistic compatible theory. And this really has to be obeyed for our framework of physics to make sense. And that's weird, because we have some problems. As you may notice, the universe is mostly matter and not antimatter, and you know that because you've not pair-annihilated. And we can look out into the galaxies and even look into the interstellar medium. Say if we were matter and Andromeda was antimatter, the medium between us still should have some annihilation with some energy we could detect, but we don't. And in fact, when we look back to baryogenesis, which is when the protons and such were created in the first second of the universe, based on what we observe, we needed to have like a 1 in 1 billion imbalance between matter and antimatter. So 1 billion antimatter particles and 1 billion and 1 matter particles. Most of them annihilated, but the leftovers are what we see today. And so it's kind of a problem to figure out where this asymmetry came from. Because if you look at your simple process, your pair production, gamma to E plus, E minus, exactly balanced. So in the 60s, Andrei Sakharov came up with conditions for baryon asymmetry. First of which is that the baryon number conservation must be violated, of course, because a proton would be +1 and antiproton would be -1. You need that to be violated to have an imbalance. And then they also need violations of C and CP symmetry. C say that say preferentially antimatter producing process is not balanced by a preferentially matter producing one. A similar thing with CP, they should proceed at unequal rates. And thermal disequilibrium, of course, is just so that things don't get balanced out in the end. I recognize I'm being very fast and loose with this. You can also replace points 2 and 3 with just a collective CPT violation. And so we're very interested in finding CP violation or CPT. Now we've already found a little CP violation, but when you do the calculations, that level, that 0.2% I mentioned, is not enough to generate the amount of asymmetry that we think we needed. So there are lots of experiments that look for more, whether they're looking in the like magnetic moments of different nuclear isotopes, or they're looking for decay patterns in the LHC, and you can also directly compare matter and antimatter to try to establish whether the symmetry is violated. And so really we're looking for beyond the Standard Model physics. And how you connect this to experiment is you take your Standard Model and you add some terms to, say, the Lagrangian. And these terms could be CPT violating, they could be various things. And it's essentially a Taylor expansion with additional parameters. And using these parameters, you can make predictions for what you'd find in your experiment. Like, for example, what is 1s2s an antihydrogen if we have X level of CPT violation? And so that's how we connect to experiment, and those are the parameters we're essentially looking to measure when we make measurements of antihydrogen. You can read this 114-page paper by Stefan Eriksson and some other collaborators from the group to learn more. So, theory aside, we're going to the antimatter factory. So this is the outside of the building, and then back there is actually where we have the inside, and so I'll show you. So the antiproton decelerator. So once we create antiprotons, they're pretty high energy, and we want to decelerate them because we want to do precision physics. And that really does not happen at high energy. We want to cool them, we want to turn them into anti-atoms. That needs to be at low energy. And so the antiproton decelerator is this giant ring that runs around essentially the whole building and slows down the antiprotons that are produced from 3.6 gigaelectron volts to 5.3 MeV. And that it uses essentially the same techniques as particle accelerators, but running in reverse. So instead of seeing a field applied in the forward direction, they'd see a synchronized one in the backward direction. And then that was introduced around 99. And then there's a further ring, Elena, to slow them down to 100 kiloelectron volts, a much smaller ring, but you can see it here. And yeah, so there's some electromagnetic deceleration. There's also just some collisions where they pass through foil or whatever. And so the antiproton decelerator is really the heart of all the antimatter physics at CERN, where there is quite a lot of it. So so here's a diagram. There's the production, there's the ring, and there's Elena. And then these, the antiprotons are delivered off to 5 different experiments you can see here: Asakusa, Alpha, Aegis, G-bar, and Base. And so 4 of these 5 are like user experiments where some external collaboration has decided they want to do antimatter experiments, and they come to CERN with this proposal, they get space. Aegis is the exception, where it's sort of a directly CERN-run experiment, but that's really just more an academic distinction. They're all kind of, they all share the same space, they share liquid helium supplies, they share the same messy magnetic environment. And so, to very briefly go over a couple of these, we have Asakusa, where they study antihydrogen and antiprotonic helium, where one of the electrons in helium is replaced with an antiproton. They want to study the hyperfine structure in the electronic spectrum. Alpha is my group, antihydrogen laser physics apparatus, where we do laser spectroscopy and gravity measurements with antihydrogen. Aegis does similar things, but they're doing gravity in a different way. G-bar is also doing gravity, and I don't know too much about them. And Base is the most precise of all these precision experiments, baryon-antibaryon symmetry experiment. They want to find out the magnetic moment and the charge to mass ratio of the antiproton. These are things that are measured very well for protons, and they're trying to measure them for p-bars. The slight problem is that the antiproton decelerator facility is a very, very noisy environment. I mean, there's magnetic fields for all the experiments, and there's a giant crane that moves around, and that messes up their precision. So a fun thing they're trying to do is trap these antiprotons, put them on trucks, and then ship them to some lab in Germany where they're going to do analysis on it. And yes?
Why wouldn't the charge to mass ratio of the antiproton be that of the proton?
I mean, it should, but some beyond the standard model of physics might make it so that it isn't, because we're looking for those asymmetries. And yeah, so they're trying to ship it. I'm not sure how that works with customs regulations and all, but we'll see how they do it. Now, yeah, so I will say Alpha, so it's my group. It is in some sense the most prolific group, as you'll see in a second, but it's also the quick and dirty approach, as people in my group described it, to doing these studies, where it's the thing that you can do fastest, but it's also not very precise. That's a slight prelude to things. Okay, so the Alpha collaboration. There's about 70 people from various institutions in North America and Europe, and that emoji did not render. Damn. It's about 30% Canadian, which was a really nice surprise to me when I got there. It's got major contributions from the University of Calgary and the University of British Columbia. In fact, there are enough people from Calgary that they can talk about specific places in Calgary amongst themselves and confuse the rest of us. There's a core permanent staff that's located there, but a lot of people who come on rotation, who are doing their PhDs elsewhere, people like me, who are there for the summer. When you have a big group like this, the leadership structure is quite complicated, where there are lots of PIs, coming from different institutions, and so they kind of, interact amongst themselves and try to make this experiment run. And so here's a brief timeline. Alpha was founded in 2005. It was essentially a continuation of the earlier Athena experiment. And in 2010, they trapped antihydrogen for the first time, which was the physics breakthrough of the year and a Nature paper. And they've, since then, 2016 and 2018 and 2020, they measured several parts of the electronic structure of antihydrogen. Those were all Nature papers. 2021, laser cooling, cover of Nature. Then 2023, the anti-gravity result that I'll show. My point with showing all of this is not to insinuate that this is super cool or something, or that Nature is the end-all be-all of scientific achievement. It's more to show that antimatter physics is an extremely good Nature bait, because it is new stuff, it's exciting stuff, and the people at Nature think that's really interesting. And it's fun when you open any thesis from the group, or my postdoc CV, and it's Nature, 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 Nature. But yeah, there has been a lot of progress. It is probably one of the most successful experiments from the AD in terms of just the results it's pumped out. So let's look at what the stack is. So this is essentially the entire experiment. On one end, you have the positron accumulator, and on the other hand, you have the catching trap for the antiprotons. I'm not entirely sure. They come in here. Here is where we do the spectroscopy for trying to find out 1s2s, 1s2p, that kind of thing. And then here is the alpha, so this is known as alpha 2, and this is alpha G, which is the gravity module. And I'll explain both of those a bit more in detail. The basic setup of the experiment is that we have the p-bar and the E+ sources. They're trapped, they're cooled, they're made into antihydrogen. We further cool antihydrogen, and then we do these measurements. So on the right, you have the control room, which overlooks the experiment and is where we monitor the situation. And then down on the left is actually the actual zone where that whole device is in, along with a lot of other just standard lab stuff. And we are almost constantly, at least through the run period from late spring to close to the end of the year, we are almost constantly running something with the experiment. And so there are almost always people on shift 24/7. They're either fixing things, running diagnoses of the experiment, or actually running the experiment itself. One of the things I learned with a precision experiment like this is that you really need to understand your system. So we have various diagnostic tools to say understand the magnetic fields in our system, and those play a really important role into the physics results, as I'll get into. So we have this web page called MyDAS, where it provides various logs for the system. This is where we start and stop runs, where say, we're trying to catch something, we're trying to mix something, that kind of thing. And this is our e-log, where we manually log a bunch of the results. I pulled this today. They're constantly adding stuff to it. You can go back and find results from 2008 in here. And it is quite tedious, I'll say. So where do we begin? We're secretly a plasma physics group, because the collections of charged particles that are positrons or p-bars are essentially plasmas. And so we use penning traps, which you can see a sort of mock-up of one here. It's a series of electrodes, and where you can apply a separate potential to each single electrode. And what we have here is there is a large static magnetic field superimposed on to confine things radially, and then a quadratic electric field to confine things in the other direction. And these particles are brought in, they're caught into the trap. There's a cold gas that they're mixed with to cool them. So they bounce off the gas particles and they come closer to the temperature of the gas. You can see here, I know this isn't a great diagram, but the settings for the penning trap. So here, say, we applied 0 voltage, here is 1, 0, 1, and obviously the voltage is continuous, so it looks something more like this. But the point is that your particles of interest would settle into either this minimum or this maximum, depending on whether they're, depending on their charge, of course. And so you have that. This is another view of what the potential looks like. So you can see along Z cutting this way, they'd be bouncing around in that center region. And then as you go to a higher radial direction, they're kind of pushed back further. This creates some very interesting motions in the trap, and we actually use those motions to better understand the magnetic environment. Because to say the frequency of oscillations in the trap depend on the local magnetic field, and that leads to different magnetometry techniques. Now, the positrons we catch from beta plus decay, they're slowed via just collisions in a foil to a few electron volts. get about 5,000 counts a second, and we accumulate them over a 100-second period. The antiprotons are from the LNR ring. One thing we can do for diagnostics is once we have caught a bunch, we can just dump it onto this imaging device and then get an image. So this is another image I pulled from recently, where you can see this like nice dense cloud of particles. And that is one of the most frequent things we're doing on shift, just trying to see if like we're even getting the particles in the first place, because it is quite complicated. All right. So we have positrons, we have p-bars. How do we make antihydrogen? We overlap those potentials for a few seconds to kind of bring them into contact, and we use a process called 3-body recombination. We have a p-bar and 2 E pluses, and they make antihydrogen and another E plus. There are 2 positrons, because the idea is that the 2 positrons collide off of each other, and one of them takes most of the energy away, because it's hard for an energetic positron to settle into an atom. Now, at 20 Kelvin, this is all still a bit too energetic. So we mixed it with really cold beryllium at hundreds of millikelvin to cool it down to 7 Kelvin. And this we use beryllium because we can laser cool it, and laser cooling is extremely effective. What happens is that you have some incoming light. It excites, it gets absorbed by exciting an electron, and then it gets re-emitted. And light has momentum, so that absorption slows down the atom, and the re-emission does give the atom more momentum, but it's in a random direction. So repeated over a bunch of cycles, the net effect is to reduce the forward motion of the atom. That is the basics of laser cooling. And so we produce these atoms, we then need to trap them. So this is kind of a diagram of the trap where sort of along here you have a big solenoid field, this is an octopole field, and then these are mirror coils. So they create this kind of magnetic environment where your atoms are bouncing around in here, they're sort of reflected by this top mirror and this bottom mirror, and kept in this cylindrical trap by this magnetic field. Now, I guess I should mention that now these are atoms, they're neutral, so they are a lot harder to trap, but they still have some magnetic moment owing to just the fundamental spins of the particles, and so that gives them some specific energy. And so using this magnetic field, we can essentially trap them in a potential energy minimum. And the magnets are produced, they're superconducting magnets, they produce up to 1 Tesla fields, and still, even then, it gets us only confinement up to half a Kelvin. So this is like still pretty warm by atomic physics standards, but it's a long ways coming from before. And we get maybe 100, dozens of anti-atoms a second, in one stacking sequence. And so we have a stacking process where we just repeat this a whole bunch of times in order to get a really big sample. And so we have this thing called the Pascal record crown to see who can get the most anti-atoms in a stack. And on one night shift, me and my partner there were able to obtain 66, which was a new record for the gravity experiment at the time. Thanks. Okay, so it's there, it's trapped. How do we detect them? So we have a cylindrical detector setup, as you can see in the bottom image. It's a lot like other particle physics experiments. Now, once the antihydrogen are released from the trap, they will annihilate with something in the detector, and that produces a bunch of charged particles, pions, where they go into this gaseous medium, they create a bunch of other charged particles, and those are detected on the outsides. And so by detecting those electrical signals, we can sort of trace back all those paths to one single point in the center of the trap where this happened. That's vertex reconstruction. And that is a single event. That's how we know something happened. The biggest problem for this is the presence of cosmic rays, which also pass through the detector and create these electrical signals. Luckily, cosmic rays are far, far higher energy than what we're dealing with. So while these lines are curved, those lines are mostly straight, and our algorithms can pretty easily distinguish them. All right, so I'm on to spectroscopy. So like I said, we want to find out what the 1s2s of hydrogen is, the 1s2p. The 1s2s hydrogen, the 1s2s transition at 243 nanometers is among the most precisely measured quantities in physics at an uncertainty of 10 to the negative 15. And it's a very small line width because it's a metastable state. It takes quite a while to decay. And so that means that its time is pretty uncertain. Its energy is pretty well determined by the time energy uncertainty principle. And so we want to find the same thing for antihydrogen. And what we do here is this is an energy level diagram where we start, say, in this state. So this is one energy level. It's split because of a magnetic field due to something called Zeeman splitting. And then these two levels are split to another effect called hyperfine structure. The point is, we can excite in a 2-photon process from here to this state, and then further ionize it and just strip off one of the positrons. And so what happens there is that then the atom goes free, it annihilates, and we detect that. And so if we're on the correct transition, we'll have ionized and annihilated a bunch of atoms. That's how we detect it. So in the 2018 paper, they achieved relative uncertainty of 10 to the -12 for antihydrogen, which is quite good. Obviously, we'd like to get a bit further with that. Here, sorry about the diagram again, but you can see another advantage of cooling, where the line width of a uncooled antihydrogen sample is quite wide, because when they're moving, that obviously you essentially have the Doppler effect, where incoming light is either it's increased in frequency or decreased in frequency. That increases the spread that you see when you're doing spectroscopy. So cooling them down, making them more still, really sharpens your line width and gives us a more precise measurement. Okay, and yeah. All right, so let's talk about gravity. The idea here is it's another way to test matter-antimatter equivalence, but this time with something from general relativity, the weak equivalence principle. You all know this. It's that stuff falls down at the same rate as everything else. It was tested in Galileo's time, famously tested on the moon, dropped a feather and a hammer in a vacuum, they fall at the same rate. And this observation is a foundational postulate to general relativity. The theory and basically every competing theory of gravity could not work without it. But we want to see if it's violated. So there is the alpha G chamber, which is here. It's a vertical chamber with a very similar detector structure, and it has a magnetic environment to balance gravity. So if you remember that trap with the 2 mirror coils, here's sort of the trap minimum. Here's one mirror to stop the atoms, and here's another mirror. But because of gravity, that potential is slightly modified. It's slightly lower in the bottom. So what we can do is essentially add an additional field and try to balance out this effect from gravity. So we can have a bias that tries to exactly balance gravity, maybe it tries to overcome it. We can try different configurations. And then in each of these configurations, we ramp down the trap, let the atoms move freely, and depending on which direction they tend to go in, up or down, we can establish whether antimatter falls up or down. So this is one place where simulations come very in handy. So you can see in the simulation for normal gravity, at different levels of applied magnetic field, you can see what proportion should fall up and down. So like if we're essentially pushing up with the magnetic field, they should all go up. And if we're at zero bias, they should it should be about, or yeah, okay, if you're canceling gravity, yeah, it should be about half. And then there are other simulations. What if it fell up? What if there's no gravity? And this is the data, and you'll see what that means in a moment. There's another way of putting the data, where depending on the bias applied, you can see how much, or what the counts were for up or down. So obviously, if you canceled the gravity a lot, you get a lot of down, whereas if you do the other thing, you get the opposite. This is actually real data. So I'm considering how much to talk about the next couple of sections because I'm short on time, but I think I can do it. So that, 5 minutes? Okay, cool. So that was essentially the experimental stack. There's a lot of complexity hidden underneath everything, including how do we get light to laser cool antihydrogen? Because it is at 121 nanometers, it's the Lyman alpha transition. And this is very hard to work with because it's so energetic that almost everything blocks light. You can't put it into an optical fiber. You also can't get a laser to start at that frequency. So what you have to do is start at a longer wavelength, say 730 nanometers, double that to 365 nanometers, and then triple that to 121 nanometers. This is through a nonlinear optical process called harmonic generation. Essentially, you use the nonlinear response properties of materials to do this. So ignore all this stuff here. But in the first stage, there's this crystal through which, when the light hits, it generates oscillations that are twice the frequency, that's frequency doubled, and then goes through down here to this argon krypton gas, where there's another nonlinear process where it's frequency tripled. Along the way, power is lost. And so by the end, we're left with like nanojoules per pulse. And it's unfortunate that it's antihydrogen. If it were like anti-beryllium, this would be a lot easier to do. Now, there's a whole thing about alignment here, which is the bulk of my project, where you send in this 365 nanometer light through a series of mirrors. It gets generated into 121, but there's still mostly 365 left over. When you output it into your system, you would like to only catch the 121 nanometer light, not the 365, and so you would like to separate them. Now, you can do this by using a lens with a highly frequency-dependent index of refraction. So like magnesium fluoride is in fact what that second lens is made out of. But then to engineer that level of separation that you want to align this whole system properly. So I was working on an alignment procedure for this. So this is kind of that part of the system, a picture of it. So 365 comes here, bounce into the gas cell. And part of the project was actually taking measurements of all this stuff to put into our simulation of ray tracing. So that model on the left is the output of some Python code to just bounce the light between those mirrors and through the gas cell to an output. And in the middle is a spot diagram showing where the two beams are perfectly overlapped. And then on the right is a configuration where they're quite well separated. And so I was modeling this and also trying to run some optimization scripts to find what are the optimal mirror angles so that we can have a separated beam. And because of these devices called picomotors that are connected to our mirrors, we can automatically control the rotation angles down to like 2 microradians of precision. But there's a problem that I'll get to in a second. So the actual optimization procedure is to place irises in the beam paths that are where the simulation tells us it should be, and then optimize so that the light passes through the irises. And so the idea is that the beam passing through the irises is exactly the optimized beam. And so that simplifies things immensely. I also wrote a control program for these picomotors, so just a GUI where it shows what their like current state is, or the angle, or like how it changes over time. You can save states, you can log states. This would have been useful, but these picomotors really suck because a certain step in the picomotor does not correspond to the same angular step all the time. A friend and I, or a colleague and I, did some measurements, and you can see here, you step this way, you have one slope, you step back, you have another slope, step the third way, you're again now just drifting in angular space, so on and so forth. These are really expensive devices, and for them to do this was very disappointing. My postdoc was not happy. But, so this is not as useful as it could be. Remote control would be nice just because it's nice to not have to be with the experiment, especially fiddling around with your fingers in a cramped space with very high energy light. But this is the best we have. So this is what we're gonna have to live with. That's my project. And now, final thoughts. Does it fall down? So the paper, Observation of the Effect of Gravity on the Motion of Antimatter in 2023, it made quite big news. You can see behind here, there's a little G symbol. So the answer is gonna be some portion of G. And I don't know, I'll open the floor to guesses if anyone wants to tell me what this number is gonna be. No takers? Okay, it is 0.75 G. And if you've taken a lab course, you'll know what's behind there. Plus or minus 0.13, plus or minus 0.16. So, like, does it fall down? I mean, yes. If you put this into a normal distribution calculator, there's a 19% chance of it being G or above arbitrarily. It almost certainly doesn't fall up. That's almost like 5 standard deviations away. There's a 50% chance of it being between negative G and 0.75 G. So, it's a cool result, but like, what gives? So one of these uncertainties is from the uncertainties in the simulation, and the other is from just actual parts of the experiment. The biggest thing is understanding the magnetic environment in the trap, which is really hard to characterize. I mean, they have done so much work to do it, but it's still a big unknown, and that's why we have these really big uncertainties. So what are the future goals for this experiment? Well, you want to better characterize the magnetic field, or you can do a differential measurement, where you put H and H bar in the same trap, you let them both fall, and then you see what the difference is. Because suddenly then, everything about your magnetic environment is the same between both, so the difference will come down to the difference in how gravity impacts them. The problem, if you may have noticed, is that the detection relies on antimatter annihilation. So we're going to need a new detection scheme. My proposal to make the detectors out of antimatter was soundly rejected. So, but there is good work on that, and it is still a very big result. So that's your answer. And then here's some fun pictures from my summer. CERN is a very cool place to be. It's a great platform for exploring Europe and getting to know a lot of cool people. I went sailing there. I went to the beach, to the top of Europe. And I would like to give a few shout outs to my postdoc Andrew, to Firaz, who I worked with on this picomotor stuff, to Fotini and Barbara, who's summer lectures on accelerator physics and antimatter. I learned a lot from and took a lot of pictures from. To the Alpha postdocs, who hurriedly arranged a welcome to Alpha presentation at the end of July, and spent about 2 hours explaining the experimental stack that I condensed into however long that was. And I also took a lot of pictures from them. And to the students from Finland, from the Helsinki Institute of Physics, who were just really awesome people to be around. And so on the left is summer interns, and on the right is also the group at large. So thank you very much. I hope you enjoyed. I guess I'll be taking questions. Yep.
Well, I'll just talk loudly then. Well, thank you to our speaker. It was a very informative talk. So do we have any questions from the audience?
How competitive is it?
Okay, so the question, I guess I should repeat the question, right? Yeah. Okay, so the question is, how competitive is it to get to CERN? It's good that you brought this up, because I actually was supposed to talk about this. The summer student program is very big, but there are also obviously a lot of applicants, and it's divided up a bit by country. As my understanding is, as a Canadian student, to get through the normal summer student program, you have to apply through the Institute for Particle Physics, and I believe there were 5 Canadians who were in through that. There's also the Canadian Institute for Nuclear Physics. I don't know if they have a program, but they had a scholarship on which I went. But there were some other Canadians. So I wasn't part of the formal summer program. I reached out to a professor at UBC who handles the Lyman Alpha part of Alpha, and they were interested in me, and so they offered to send me to CERN, and so I was there sort of on their, that special arrangement. And there were a couple of other people who also had their own arrangements, separate from the standard summer program. So, IPP, very competitive, I have to assume. But if you can find someone you're interested in working with, that's interested in sending you, then that works out really well. Like I said, the big Alpha are Calgary and BC. And then for other parts of CERN, we have presences all over the country. Obviously here at UT, we have a very big Atlas group. So, yeah.
Any other questions?
Yep.
What other work did you do at CERN?
What other work did I do? I mean, to be honest, the ray tracing simulation and writing the control program were the bulk of it. Then there's obviously shift work, as I kind of alluded to, where sort of everyone on the team has to indicate their availability for shift, and then you get a shift schedule. It shows you, what days you're on, whether it's night shift, or morning shift, or whatever. And so I was doing a fair amount of that, and a lot of that is just sort of characterization of the experiment. So one night we were essentially doing magnetometry in the thing the whole night, testing different parts of the electrodes. What's the magnetic field here, there? Is it stable? Is it drifting compared to when we did it a few days ago? That's a big part of it. There was also mixing tests that I partook in. It's a very labor-intensive process, and I really do think there is a lot of room for automation and would save a lot of trouble and a lot of time. But I mean, who am I to say? There was this other small thing I was working on where I was working on some electromagnetic simulations for the future hydrogen experiment they're doing in Vancouver. Just simulating vendor designs for that. Yep.
You mentioned you use a lens to differentiate light with different frequencies.
Sorry?
You mentioned you use a lens to differentiate light with different frequencies.
Yeah.
Like long or triple frequencies and stuff.
Yeah.
I'm wondering, do you just order that from somewhere, or
Yeah.
do you make them?
It's probably Thor Labs. I mean, they have basically every optics component on the planet. It's not it's the material that's special, magnesium fluoride, but if you can get your hands on an industrial process for that, you can make it into a lens. And we put that at the end of the gas cell, and if the incoming beam is so correctly positioned, then it'll nicely separate the two frequencies.
Do you know what's the price?
Price? I mean, we can look it up right now, but that's probably gonna, if I had to guess, a couple hundred. I mean, that's gonna be an expensive
And also you mentioned you need to align, like alignment really well.
Yeah.
Is that like angle specific or like position?
So the positions are I can actually show you this on the breadboard.
And I know you should probably just align to the center.
Yeah.
You should
So
be able to find-
like generally in optics, you have things fixed onto a breadboard, so all the positions here are fixed. But then you can play around with these little motors or automatically control them if they have the capability. That changes their rotation angles essentially. And that's the main alignment thing we're doing.
Yeah, but I mean, like, when the light hits the lens,
Mhm.
doesn't matter, like, where it's
Oh, like center optic or not.
The angle that matters.
It's mainly the angle. I mean, you don't want it to really be off center that much if you can help it, but the angle's the primary thing.
Maybe one more question.
All right.
He described it with potentially causes a bit more for the gravity experiment. So it's you get antimatter that falls down, and that's the annihilation of the
Yeah. So that whole like annihilation detector to gas to electrical signal apparatus is around both the spectroscopy experiment and the gravity experiment. And so when the antiatoms are released, wherever they end up annihilating, if they fall down and annihilate here, fall up and annihilate there, that they will create pions, they'll be detected as electrical signals, and then our algorithms reconstruct the various signals to a vertex. And that is a position in space that then we can like, do further analysis on.
So I think we're running a little short on time, but I think Aryan will be around in a few minutes after we give him a question.
Yeah, I'll be around, don't worry.
So yeah, let's all thank our speaker one more time. Thank you everyone for coming.